Question 6. Ammonium chloride when dissolved in water can act as a weak acid, shown by the following equation. Figure 1 shows a graph of data obtained by a student when a solution of sodium hydroxide was added to a solution of ammonium chloride. The pH of the reaction mixture was measured initially and after each addition of the sodium hydroxide solution. Suggest a suitable piece of apparatus that could be used to measure out the sodium hydroxide solution. Explain why this apparatus is more suitable than a pipette for this purpose. Well, a suitable piece of apparatus is going to be a burette. Reason being, it can deliver variable volumes, unlike a pipette which cannot. So burette, as it can deliver variable volumes. 6.2. Use information from the curve in figure 1 to explain why the endpoint of the reaction would be difficult to judge using an indicator accurately. So if we look at the endpoint of this reaction, we can see that the endpoint is very, very gradual. The change in pH is very, very gradual. So we can say the change in pH is gradual. Okay, what we're trying to say by this is that it's not rapid at the endpoint, therefore indicator will not change color rapidly. Indicator would not change color rapidly with a few drops of, in this case, NaOH. With a few drops of NaOH. I've seen a couple of these questions where it's like, use information from the curve to explain why the endpoint is difficult to judge accurately. The key ideas in this question is that I like to generally repeat is that the change in pH is gradual, or is not very rapid at the endpoint, hence the indicator will not change color rapidly, or you could say indicator will change color over a range of volumes of sodium hydroxide. Therefore, it's going to be extremely difficult to judge it accurately because the indicator will change color over a range of volumes of sodium hydroxide, or you can say indicator will not change color rapidly with a few drops of NaOH, sodium hydroxide. 6.3. The pH at the endpoint of this reaction is 11.8. Use this pH value in ionic product of water to calculate concentration of hydroxide ions at endpoint of reaction. Well, firstly, let's construct the equation of Kw. We know Kw is going to be equal to H plus OH minus, and we know to get we've got the pH at the endpoint of the reaction, so we can quite easily find the H plus. H plus equals 10 to the power minus pH. Therefore, that is equal to 10 to the power minus 11.8. We're given pH in the question, and that is 1.58 times by 10 to the power minus 12. 1.58 times by 10 to the power minus 12. And that is the concentration of H plus. And now we can rearrange this because what we're trying to find is the hydroxide ions, this, so we need to rearrange it, so we get OH minus equals Kw divided by H plus, and we are given Kw in the question, 1.0 times by 10 to the power minus 14, divided by 1.58 concentration of H plus ions, which I just worked out using the equation H plus is equal to 10 to the power minus pH, 1.58 times by 10 to the power minus 12, and then we get the answer that we need. Six 0.33 times by 10 to the power minus 3 mole per dm minus cube. That is for 3 marks. The hard part for this question is just knowing that it's given us pH. We need to find a concentration of H plus ions. I'm going to use this equation. H plus ions is equal to 10 to the power minus pH. We've got the pH, find out H plus ions, rearrange the equation, OH minus, and then substitute the values in for 3 marks. And then 6.4 and 6.5, 2 calculation questions, just like 6.3. It says expression for the acid dissociation constant for aqueous ammonium ions is that. The initial concentration of the ammonium chloride solution was that. Use the pH of this solution before any sodium hydroxide has been added to calculate value of Ka. Well, we need to work out the pH so we can find out the concentration of H plus minus ions or H plus ions, and then it's pretty easy from there. So before any sodium hydroxide has been added, we scroll up the volume of sodium hydroxide added before any has been added, so that's when 0 has been added. And if we zoom in here, it is 4.2, 4.4, 4.6, 4.8, 4.5, so it's going to be 4.6 because they go up in 4.2s, 0.2, so it's going to be 4.6, and now we can find out concentration of H plus ions. H plus equals 10 to the power minus pH. For H plus is equal to 10 to the power minus 4.6, which is equal to 2.51 times by 10 to the power minus 5. Okay. Now let's rearrange this equation to find out the value of Ka. Actually, no, it's already rearranged. But what we can, as the assumption that we're going to now use is that Ka, instead of equals to NH3 in square brackets, H plus minus square brackets, it's going to be Ka is equal to H plus squared over NH4 plus. That's the assumption we're going to make. And then we get H plus squared, which is H plus, which we worked out by using H plus is equal to 10 to the power minus pH, and then we find out the pH because we knew in the question before any sodium hydroxide has been added, and then that's 0, and then it reads a value of 4.6. So it's going to be 2.5 times by 10 to the power minus 5 divided by 2, because that was the initial concentration of the ammonium chloride solution. So 2.51 times by 10 to the power minus 5 divided by 2, 1. Squared is, can't believe I forgot that, squared obviously, because what assumption we made is that these two NH3 H plus minus becomes H plus squared. That's the assumption. So it's going to be that squared, so that times by 2.51 10 to the power minus 5, and we get 3.15 times by 10 to the power minus 10 moles per dm minus cubed. And then 6.5, a solution contains equal concentrations of ammonia and ammonium ions. That's very key. use your value of Ka to calculate the pH of the solution. And then this is if you were unable to calculate value of Ka, but we did calculate value of Ka, so we don't need to know that. Ka is H plus squared divided by NH4 plus. So let's write down the original equation. Ka equals NH3 plus NH3 H plus minus NH3 H plus minus over NH4 plus H4 plus. Well, we know these have equal concentrations of ammonia and ammonium ions. So if they're equal, let's say we've got 2 times by H plus divided by 2, well, these will cancel out, and that's exactly what's going to happen here because they're the same value, they're equal concentrations. So what we get is Ka equals H plus, ignoring the minus sign, that's to trick you out, is equal to H plus. Now, how would we work out Ka? Well, we know Ka is that. From 6.4, Ka is that. So we know H plus is equal to Ka. H plus is equal to 3.15 times by 10 to the power of minus 10. 3.15 times by 10 to the power of minus 10. And we know pH, to find out pH, is equal to minus log 10 of H plus. Therefore, it's going to be minus log 10 of 3.15 times by 10 to the power of minus 10. Log 10, 3.15 times by 10 to the power of minus 10. And I get 9.50. It does say explain your working, but you guys know what you say. I would write equal concentrations of ammonia, ammonium ion, therefore NH3, NH4 plus cancel out. K is equal to H plus, therefore you can say minus log Ka is equal to minus log H plus. Therefore pH equals minus log 10 of H plus, which is minus log 10 of 3.15 times by 10 to the power minus 10, which will give me that. So just a bit of explanation, but it's just going to be time consuming if I write the explanation. I'm pretty sure you guys would know what to write. Just show the cancelling and then show the substitution and explain why. And that is the end of question 6.